Oh, good. So this was work that was actually done by an intern at CNES called Ahmed, and me and Denis were his supervisors, mainly actually Denis. I just sort of helped them out on the OTB side and on the machine learning side, but they were behind the whole idea in the first place. So if you don't like the idea, talk to them. The idea in itself is, well, we have all this great Sentinel1 data. There's actually a lot of interesting features that we can extract from SAR data, particularly interferometry and polarimetry. And so the question, I guess the scientific question that we try to answer is, how can we best use this SAR data to achieve land clever classification, like we see over here in the slide, where we've divided this image into 5 different classes. So yeah, go on. So I don't need to go through this because Thierry already gave us a very good introduction of what Sentinel-1 is. So just a few reminders on the parameters of the satellite, but we can skip through this pretty fast. So we're interested in looking at the polarization of the radar signal that comes back. So as you may know, a radar signal is a wave, an electromagnetic wave, and as such it's polarized. There's different types of polarizations. So we usually use elliptical polarization, and it has 2 directions, the horizontal and the vertical direction. So move on. Basically, we're going to be emitting in the vertical direction and then receiving in both directions. And then by using this information, how much have we emitted compared to how much we've received in either one of these polarization directions, we derive information about what happened at the surface when the wave actually went into contact with the surface. So go on. And as we could see, when a radar wave reaches the Earth's surface, depending on what kind of land cover or what kind of material is at the surface, the wave is going to behave very differently. So on a very flat surface, like water, for example, it's all going to bounce right back in the opposite direction. If we have a little bit of roughness, we're going to get this sort of surface diffusion where some of the wave is going to come back to the sensor. If we have right angles in our scene, especially buildings and the foot of trees and stuff like that, we're going to get these double bounce effects. And on canopies of trees or stuff like that, we can get this sort of volumetric diffusion. And so depending on exactly what kind of type of diffusion we're expecting here, we're going to see that the VV, so vertical, and VH, vertical-horizontal, backscattering coefficients are going to be different. So this leads us to believe that this information might be valuable for classifying these different types of surfaces. And here's a bit of an illustration of what we see in such a VV-VH images. So Google Earth, and you can see the water is, for example, very, very dark, and so urban areas are going to pop out a lot more. But that'll be for the algorithm to figure out. So just to wrap it up on our goals here. So it is using Sentinel-1 images, fusing them all together, so using time series, and then train an AI model to be able to automatically classify each pixel in the time series. So in order to do this, we divided our work into 2 parts. The first part, which is really about the data in itself. How do we start off with raw, quote unquote, VV and VH images, and then bring them all together to compute a bunch of indices and stuff like that, orthorectify them, and then produce this massive file, which we're then going to use as a data for the machine learning model, which we'll talk about later. So first about the data processing part. So we did a calibration, which involves performing some kind of radiometric correction depending on the local incidence angle of the radar signal. So that's pretty straightforward. By the way, all of this was done thanks to the SAR processing capabilities of OTB. Just over here. So here's a bit of an explanation of what interferometry is exactly. I don't think this is really necessary here. What you need to know is it's a method to derive how much the Earth has moved between two successive dates. If the signal has a strong coherence, we can do this using the phase. But yeah, you could also just see this from a machine learning perspective as more features, more information to be ingested by the model. And here as well, more features and more information ingested by the model, which have been developed by different papers throughout the years, different ways of combining these polarimetric bands together, kind of like what we do for NDVI on the optical side. So you also have all these different indices, some illustrations of the indices. But once again, we're just going to feed all this to the AI and see what it figures out. So this is what it looks like, our huge table of features. So each pixel gets one of these bad boys. So you have 29 dates, and then all of the different features, so 10 different information features for each date. So it ends up to be quite large for each pixel. Yeah, and another very important step, which actually took us a bit of time, which was to orthorectify the image, because we needed to superpose it with the ground truth database, which we took to be Corine and line cover. So when we need to superpose these two products, we need, I guess, them to be in the common geometrical space. We decided to bring the S1 image into the same projection as Corine by performing orthorectification. And this was also done with OTB. All right, so once we have our data ready, we can move on to the data analysis part, the machine learning part. So go forward. And here, once again, we used OTB for this part to extract the statistics of each polygon, select samples, extract the samples, do the image statistics for normalization purposes, and all of those cool things that the OTB machine learning module, future OTB machine learning module will allow us to do. And then, I mean, okay, we didn't go for very advanced AI methods here. We went for the good old-fashioned random forest because it was an internship, and the goal was really to explore and not to challenge the intern on doing deep learning. And so here we go. We can go and look at a few results. So we chose two different study areas. One was the south here of France. The other one, if you go on, the other one is in Paris. And so we tried different combinations of training and testing in these different various areas. These were the classes that we considered. So the basic CLC description is just the 5 levels. We tried it out with both levels of complexity, obviously getting way better results on the 5 classes. But this is also just to give you a bit of an idea what kind of subclasses could also exist, and for future versions we might also go towards more complex nomenclatures like this. This is just the standard machine learning evaluation. So we calculate the overall accuracy, precision, recall, and F-score for the various classes. Yeah, so here's some results. I mean, we're going to skip through these pretty fast. The main thing that we can look at here is the fact that overall our accuracy is pretty average, close to 0.5, slightly below 0.5. So we're not really doing a great job at recognizing every single pixel. But if we look at the max F-score column, you can see that some of the classes occasionally are very well recognized. And this is F-score, not precision or recall. So it really means that it's well isolated from the other class if it has a high value. So for example, in this first case there, you can see that water is very well isolated. Not too surprising if anyone's classified SAR data before. Water is very clearly visible. And so yeah, just skip through these because there's a bunch of slides here with all the results, and honestly they're pretty similar. And I have an overview graph with all of them. Okay, it's just yeah. Here we see a bit of a visual analysis as well of our classified results. So the Google Earth image for just visual reference, the ground truth. So this is what we consider to be the ground truth polygons of Corine. So as you can see, they're quite coarse, quite large compared to the resolution of Sentinel-1. And then on the right, we see the results of our classification over there. So you can see we have a lot more details in the classification map. It seems like it's able to distinguish that two different pixels are different. But then does it really get the right label? Not all the time. On the water, it's good. But actually we can see on the airport runway that it's confused the runway with water. And if you remember what I said a few slides ago about the fact that when a radar signal comes into contact with a very smooth surface, it's going to bounce right away back into space. In that sense, physically, the runway is not too different from the water. So it's not surprising that this algorithm confuses them. It's because it has no notion of the context of the pixel, which would be extremely helpful to distinguish these two classes. So it makes these big mistakes on the whole entire object, but nonetheless, it's able to distinguish the border of the object with the surrounding objects. So as a segmentation tool, it's not too bad. In terms of semantics, it's not that great. That's the overall analysis here. And when we push it to way more levels of classes, we can also see that we still get kind of this nice spatial detail. We can see things that you can't necessarily see in the CLC. And also, I mean, if you look at the base radar image, it's also, unless you're a bit used to it, it's very difficult to tell what you're actually looking at here. So I think for people who don't know much about radar, this could be very useful to help in analyzing. Yeah, so this is the overall table of our sort of best performing model. And I think the main thing that we noticed is really the humid zones were completely missed out. So this is sort of swamps and class a bit like that. I mean, two things about this class: it's very rare, and especially compared to the other classes, so it's going to be a minority class, which is always harder for machine learning algorithms or AI algorithms in general to distinguish. So it's the first problem. And the second one is that it's not very clear exactly what the definition of a humid zone is, and these humid zones actually change a lot throughout the year. So some dates they're going to be completely full of water, other dates it's going to be completely full of vegetation. It's really hard for the model to really associate one behavior with these humid zones, especially when you have a limited amount of training data on them. Just looking at the humid zones in the south, it's not going to help you at all to understand the humid zones in Paris, because the phenomenology is very different in the two areas. So I think we would probably just need more data to get that class right. These are a few of the different tools that we used, obviously, OTB. Yeah, go on. And I'm going to wrap it up with a bit of a conclusion here. So we got pretty average performance, but I would say we did pretty well considering that it was an intern. So we noticed that the geometrical contours of the objects were quite well defined. There is still, though, some global noise, which we expect is linked to the noisy behavior of SAR data in general. So it could be speckle effects, stuff like that, double bounces, we don't know. But there is a little bit of that underlying noise, so that could be smoothed out as well. We didn't try. And so the main future directions for this kind of work we felt would be to go bigger, so go national at least. If we increase the size of the database, we're going to get a lot more variability in our training classes. We're going to cover a lot more different types of phenomena. So we should be getting better results, and we can take inspiration from what's already been done with Sentinel-2 by the SBO, where they did this eco-climatic stratification strategy where you cut the territory up into different eco-climatic areas, and then you use each one of those as a training set, and you only evaluate that model in that same eco-climatic area. So you have a model that's specialized to the behavior, to the climate of one place in France or in the world. The other really cool thing for future directions, maybe with the future AI capabilities of OTB, this would be a cool example where we could do just basically the same thing, but switching out the random forest for CNN or some other kind of deep learning model. Hopefully with the spatial context around each pixel, it would be able to get a finer semantic description of the classes. And finally, I think this was also a bit brought up by Thierry in his presentation, the fusion with Sentinel-2. requires having exactly the same pixels and everything, but because we have this ortho rectification, we have S1 tiling, we can actually do this in a very straightforward manner. So we could have aligned Sentinel1 and 2 time series and give them all to the model instead of just one modality. So yeah, that's it for me. Thank you very much for your attention, and if you have any questions.